Okay, you see the screen. If I can see the chat here. Okay, perfect. So this will be the next lab. Um, I haven't uploaded it yet, but I will in just now in the afternoon. So the idea of the lab is quite similar to the previous lab, where you will have one notebook with some examples and another notebook where you have to do something a bit more complicated. Okay, so what we are trying to do here is to solve the advection equation with boundary conditions using finite differences and the method of lines. So we are again discretizing in space, then evolving in time, calculating the spatial derivative to evolve in time using Runge-Kutta, but now we are not using periodic boundary conditions, but we are using some conditions at the extremes solution. Right? So this is the idea of what we want to do, right? Again, this is our equation in this case. Later on in the homework, you will actually have to work, for example, with the wave equation. Not so much with the advection equation, but as you know, the wave equation is actually two advection equations going in different directions. So this here, what I want to show you is what we are expecting to simulate. Okay, so we have this equation here, and we have some boundary conditions at the boundaries, right? Here we have an initial data which is completely flat, zero everywhere, but then at the left we will put some condition, which in this case is a sine wave. Okay, so we expect that at the left the solution goes like a sine, and this starts propagating because we have advection to the other side. And it's very important to take into consideration that we can only impose a boundary condition on the left. We cannot do it on the right because waves are coming from the left to the right. So whatever we put on the right would actually have to go outside. Whatever is on the right is decided by what is coming and is trying to go out of the solution. And you will have to be very mindful of that later on when you are working with the wave equation, or you have two solutions that are trying to go in different speeds. So when you put some boundary conditions, you have to be very careful of what you do, because you cannot input a solution that's going outside. Okay, you have to always put what's going in, right? So in this case, what we expect is something like this. Okay, so here at the boundary we put a sine wave, right? And it just goes up and down, up and down. And originally we had a flat solution. And look at this side, we don't impose any condition. We just let the wave get out the of the region, right? As usual, we will represent some interval, in this case 0 to 2p, with certain amount of grid points and which are evenly spaced, right? And we are defining now our derivative operator or finite difference operator. And in this notebook, we will only work with the second order operator, which is simpler. And then in the actual homework, you will work with the fourth order. We will need to create the function that does the operation, that does that operator, and use the appropriate coefficients at the extremes. But don't worry, they will be provided, right? So this is the third order homework. You will be given the coefficients, so you do not need to calculate them, but you need to actually implement the method, right? So what we want to do is for our operator to satisfy summation by parts. So I want to ask you if you understood this part about summation by parts, what we are trying to achieve, uh, what we are actually doing here when we ask for this derivative operator to satisfy summation by parts. So if someone in the chat could say, okay, yes, I understood this part, or no, I would like to review this to understand what's going on or why we need this. Because what we have here is a property of derivatives, right? Where if we have two functions, u and v, right? And we do this operation where we multiply u by the derivative of v, and then the derivative of u times v, and we integrate in the region, we will actually get the solutions at the extremes, right? The, the difference between the solutions at the extremes. And what we are trying to achieve here is to have that same property to hold for our differential operator, right? So we need to define some internal product here, numerical integral product that will be the analogous or for integration, which is the internal product that we have here. And we want this condition to satisfy, right? For some h that we need to define, and from some d that we need to define, right? And we want to do this just to make sure that our energy is well defined and that we can guarantee stability. Because in our energy, we will actually have this equation, right? This is the equation for the energy, is 1/2 of the L2 norm of U. And when we derive this over time, we will get a term that has to do with the time derivative, which will transform into a spatial derivative. And then we will get that the derivative of E over time will be the difference between the solution at the extremes, the square of the solution at the extremes of the solution. And we want this to be hold as closely as possible. So that is why we are trying to preserve this property of the operator, so that when we do this operation numerically, then we get exactly the same. So this is why here we are defining some second order operator and some inner product matrix, right? So this will be the inner product, the way of calculating the integral iteration. So this is basically the trapezoid rule to calculate the integral u in the region. So it's very important to have this 1/2 at the extremes, and this will be our matrix for calculating finite differences. And you notice that basically everywhere we have some central scheme, right? The second order scheme, and then at the boundaries we actually take first order derivatives. So we will lose a bit of order in the derivatives in the in this part of the notebook. What we will do, and this is something that you will have to do later on when you do the fourth order case, is to try to see if this property actually holds, right? So if we apply the d operator to some v and to some u, and we do this operation here, we multiply by the matrix H, right? And we do this operation if we actually get the values of the product of u and v at the borders, right? The difference between at the boundary, right? The difference between these two products. So this is exactly what we are doing here and what we will have to do later on with the fourth order. Here you will have to find the H matrix BAT fourth order calculations. And here you will have to use the fourth order operator. And what we are doing here is defining some U and V values that are completely random, right? So U and V are just random numbers. Right? If we print here what we have for U, we have just some random garbage values. And what we want to say is that if when we calculate this here, which is this operation here, this matrix operations here, we get exactly the values of the boundary. And we expect this to be 0 or very close to 0 because we will always have some numerical errors. And in this case, this is very close to 10 to the minus 16, which is essentially the precision that we have with the computer. So if we get a value close to 10 to the minus 16, it's telling us that this is essentially just machine error. There is no, this is actually up to now we just defined the operator. Now we need to impose some boundary conditions at the extremes, right? So we will get some boundary condition on the left and some boundary condition on the right. But in this case, the boundary condition on the right will need to be ignored because we don't actually have to impose anything there because the waves are propagating into that direction, right? And this is the term that we want to use on the left, right? So notice that we need the propagation speed, the delta x, and the value of the h11, which is the first element of the inner product matrix, right? Here we impose some boundary conditions. And what we expect this to do is just to add some decay term to the first part, right? We are not telling the first point to be exactly g of t. What we are actually doing is introducing some kind of decay equation. So we expect this to decay exponentially to gt, right? So we are kind of guiding the point to be close to gt. We are not saying you are gt. We are saying you need to get as close as possible when you evolve in time, right? So this will give some exponential decay for the first point, so it gets close to the boundary value that we actually want to achieve, right? And here we can actually try to see the energy conservation part of this. So we can actually do the energy conservation of the system. And what we will see is that the energy, if you solve this equation and we develop it, right, which it's quite easy to do, you just need to use here the fact that we are using summation by parts operator, so you can get just the boundary elements, and then you do a term here with the SAT, which is also easy to do because we have this delta, so we are also working just with the boundary. And these values here, this C, this H, this delta X, are just there to cancel out the appropriate terms. And we will get this equation here for G energy. So we can write it actually this way, the derivative of the energy. So we see that it will be G in T squared minus UN T squared, right? The boundaries, minus some term here that has to do with the difference between the value that we are trying to impose, g and t, at the boundary, and the actual value that we have at the boundary, right? Which is not the same, because we are trying to get there exponentially. So the derivative will be at least less than what we are expecting there. So this will give us the stability. This will tell us that the energy will not grow more than it would grow otherwise given the initial condition. Because here the energy will grow, at least for some time, because we are entering stuff inside the solution, but we just don't want to put more stuff than we wanted to enter initially. So recall here the value of the actual value of the derivative of the energy is equal c over 2 times the difference between the values. And here, let me see, maybe I need to correct this. So one of the two is actually wrong here, because there is a 2-factor missing here. So let me check these equations later on to put, but essentially what we will have is exactly the same minus some term that is very close to 0. Let me fix this. I don't know why the Zoom seems to have crashed. Screen sharing de vuelta. Just 1 second. My Zoom session has some issues. So I will verify this equation later, so it's working perfectly. Okay. So this is what we actually want to achieve, right? For now, we will present an example of how to solve this, and we will show two methods that do exactly the same thing. One is more illustrative of how to do things, so we will create this entire matrix and do the calculations using the matrix. And the other method is closer to what you will actually try to implement when you actually are trying to do some code, which is just to do the calculations step by step instead of relying on some gigantic matrix. So this is the same as you were doing in the one before, right? So you are receiving the operator, the propagation speed. Here we are receiving some function, which is actually the boundary condition that we are trying to impose. And in this case, first you do the find difference operator to calculate the derivative, and then you add this term here, which is actually the SAT term. So this part here is the one that's telling the solution. At the last point, okay, also, besides the solution that you have to do with the wave equation, you need to have some exponential decay that goes to the value t with the parameters that this g function needs. This is exactly the same. It's just that we are using here this formalism. So we are taking some derivative vector where we are storing the solution, and we are calculating the center differences like this, right? So we take the solution 2 points, 1 point to the left or to the right, 1 point to the left, we subtract them, then we multiply by 1 over dx and by 1/2, and here we have the propagation speed, right? And then at the boundaries, we do exactly the same, just that we use one less point because we have one less point to use here the first order derivative, and here again the first order derivative plus the SAT term. So this here is exactly the same that we have right here. This is the SAT term, and this here is exactly the same than this here. When you see this at symbol with anywhere in Julia, when you see some at, this is a macro, right? It's not actually a function, it's a macro, it's some way of programming also in Julia. So when the macros essentially work over expressions and create expressions and manipulate them. So here when we use this macro at dot, it's actually putting broadcasts everywhere where it's needed here. So here maybe we need some broadcasts to multiply, to do the subtraction, stuff like that. So just to not be putting dot here, for example, a dot, and maybe we need another dot here. When you use this macro, it just adds all the broadcasts that are needed. So this operation is point by point wise instead of being by the whole vector. And now we will do some, we will give some initial data, which in this case we are giving us 0. But here you can put some wave here at the beginning, some whatever you want to put. And now we are creating some boundary conditions, right? In this case, we are using a sine wave, but you can modify this right here and put whatever you want. Just try to put it here and try to ensure that you at least have continuity with the initial condition. And then you have some integration time, some frequency that we want to use for this sine wave. We create the operators again for the problem that we are trying to solve. We define some parameters, the delta t, and again we will simply evolve using the differential equations package in Julia using these two approaches. One will be the matrix approach, and the other one will be the summation by parts approach, the direct approach, right? So we solve both equations, and now we plot. Plotting again here. So as you can see, both solutions are exactly the same. It's the same operation, and you can see how the sine wave is actually entering the solution, right? And you may see some weird oscillations starting with the first when the wave first enters. So you see that the shape is not perfectly smooth. This is to be expected because we are actually entering like a discontinuity. So this is a sine wave that's very abrupt, and suddenly the function itself is continuous, but the derivative is not. So again, recall that we can do a Fourier transform, for example, of the solution, and we will have different wave packages moving at different speeds. So this is the effect that you are seeing in that region there, right? And we can put some other solution here. For example, we can put, imagine that we put something like, we put a sine plus cosine t times w times 2, right? And we do this, and we probably have some issues here because there will be a discontinuity at the beginning. Right, so I wrote w instead of omega. Yeah, and so here in this other plot, we are seeing is the energy of the solution that you can also plot. And we see that as the solution is entering, we start getting more and more energy until we have a point where there is some balance between what enters and what goes out. If you zoom in here, you will have some maybe some little oscillation which has to do with the difference between the 2 points because they are not exactly the same. There will be a small difference, so you will have like a very very small sine wave that's oscillating here if you do some zoom. But you can see how essentially once the system stabilizes, we have some constant value of the energy. So here, for example, you see that there are some waves here that are moving in a strange manner. This is exactly because we have entered some initial data that's not continuous, so there is a lot of oscillation there by the in the Fourier transform. But because there's a lot of dissipation, maybe the code did not break, but you can see it here. But later on, you see how we are actually entering the correct solution. So this is working just because this will probably not work with higher order operators. It's better if you put some initial condition that fits nicely with the initial, right? And also you can change the frequency here and be careful because if you use too high of a frequency here, you will start getting waves propagating in the other direction and you will not actually get a good solution. So this is an overview of the notebook that will assist you to do the homework. Okay, uh, it's quite short, it's quite simple. The homework in itself, right? You will need to create the operators using the right coefficients, but we are giving you the coefficients because it doesn't make much sense to just. I mean, if you want, you can always try to derive them yourself, but it's better just to know they exist and understand why they exist using the second order one, and then the just applying the formula that someone else calculated in this case. So we are giving you the coefficients of the derivative at the extremes. We are giving you the central scheme, also the second order central scheme that which you already know. And here we are giving you also the matrix to do the internal product, right? So the matrix will also be ones, but instead of being 1/2 and 1/2, it will have all these values here before. And you will have to work with the wave equation. So you will have to be careful here because you will have two modes in the wave equation, one that's going to the left, the other one is going to the right. So when you impose boundary condition to the u and v that you are using in the previous one, you need to be careful to only, you need to decompose the u and v in the correct eigenvalues and only impose boundary conditions on the part of u that's entering and not on the part of u and v that's entering and on the part. You cannot find this yet. I will update it. I will upload it in a bit because I was just translating this from Spanish to English and I couldn't upload it yet, but I will upload it in the afternoon. I will upload it just as is in like around 1 and later I will correct some stuff so there again the mistakes here in the value of this integral I will correct them now and try to put the correct value. I'm not sure if there is a mistake there or before. The energy estimate, I think yeah, this is okay, right? Echo? This one is okay. Yeah, so the other one is the one that where I made a mistake, which usually happens because there are some there is some one half number here that's missing. Probably there is a C/2 here, C/2 here, and I lost it, and so I am not getting the correct solution. So this is essentially what you will have to do for this lab. I don't know if you have any questions about how to do this, or questions about the previous lab, questions about the homework that you address. Or has anyone had any trouble, some issues with the previous lab, for example, or want to understand a bit more of how this one works? Okay, so so in that case, if you don't have any questions, about the last lab, I couldn't find the wave equation file. Okay, so that should be available. Um, Here. Ah, so labs here, wave equation supplementary. Click here to download this notebook. Yeah, this you can find it here. You can always download the notebook from there. Okay, so I will be updating it here. I don't know if we will keep the enumeration like this. Probably yes. Maybe confusing with the first videos, but later on we will update the lab 4 and lab, yeah, the lab 4. Which, as you can see, is not much more difficult than the previous one. If you did the previous one, this will not be much of a challenge. It will be essentially the same thing, changing a bit the operators and imposing the boundary condition with a very simple case. Okay, so if there are no any more questions, we can close the class here and we can continue tomorrow. Okay, so in that case, I will here recording.